Evaluate the integral from 7 to 16 of 1 over the cube root of x minus 8. At first glance, this seems like an innocent integral, but it turns out that it's actually improper, and recognizing it is the issue. If x is equal to 8, then we'd have division by 0. And so because our interval has 8 in it, then we have to actually label this as an improper integral. Because it's improper, we'll have to introduce a limit. So what we'll do is we take the interval, which is from 7 to 16, and break it into 2. We'll go from 7 to 8, and then we'll go from 8 to 16. And so when it comes to allowing x to equal 8, we can't do it. And so we introduce a limit and let some variable approach 8. As a technicality, we'll let t approach 8 from the left-hand side on the first integral because it's approaching from smaller numbers. And we let t approach 8 on the right-hand side in the second integral because it's approaching from larger numbers. And we have to do these two integrals separately and the two limits separately. So let's take a look at that. Let's just deal with the integration part first. Let's perform the integration. How do you integrate 1 over the cube root of x minus 8? Well, if you do a substitution, it makes it just a little easier to see. By letting u be equal to x minus 8, then you'll have du is dx. And so you'll be looking at 1 over the cube root of u. And that's better written as u to the negative 1/3 power, so we can use the power rule in reverse. Add 1 to negative 1/3 and you get 2/3. So the antiderivative of u to the negative 1/3 is u to the 2/3, but instead of dividing by 2/3, we'll multiply by 3/2. So that's just the power rule in reverse. And that's just a little scratch work off on the side to help us figure out what this integral is. And now we'll go ahead and go back to our integral here and replace the u with x minus 8. So we're looking at 3/2 x minus 8 raised to the 2/3 power. Alright, great. Now we treat it as indefinite just so we can then go back to our current integrals that we're facing and now plug that in. And so we'd have to plug a t in and plug a 7 in to our first integral, plug a 16 in and plug a t in to our second integral. So we'll be looking at these two limits now we need to perform. Let's take a look at that on the next slide. So let's go ahead and perform the limit. Evaluate these limits. So what happens as t goes to 8 from smaller numbers? When we have t minus 8 to the 2/3, t going to 8, that's just going to go to 0. When we have t minus 8 to the 2/3 on the second one, now we're going towards 8 from positive, from numbers that are a little bit larger than it. It's still going to 0 though. It's the fact that it's a positive 2/3 that makes this end up converging to a real number. If it had been a negative exponent, then the integral would have diverged. Now let's deal with what's left. We have the 7 minus 8 and the 16 minus 8. These guys are raised to the 2/3 power. So 7 minus 8 is a negative 1, and 16 minus 8 is an 8. These guys are raised to the 2/3 power. And so negative 1 to the 2/3 can be thought of as negative 1 to the 1/3 and then squared. 8 to the 2/3. Take it to the 1/3 and then square it. By doing that, we can then see that 8 to the 1/3 is a perfect square, a perfect cube, that's a 2. And negative 1 to the 1/3 is a perfect cube, that's a negative 1. And then what we're going to do is now square these guys. We'll take 2 and square and take negative 1 and square. Now what happened was the 8 had a positive coefficient, and the negative 1 to the 2/3 had a negative coefficient. They both have 3/2, and so what I did is I factored out the 3/2 and I rearranged it so that the positive one is first, and then we subtract the other guy. And so this will end up being our final answer once we're finished. We have 2 squared, which is 4, negative 1 squared, which is 1, and we subtract these in the order of operations. Subtract 4 minus 1, you get 3. And then 3 times 3/2 is our final answer of 9/2. So be on the lookout for when you have an interval that involves a place where your denominator is 0. Because then you have to break it into 2 integrals. It won't always converge. This one here converges, but this is the one time where you have to worry about recognizing whether or not it's improper. It doesn't look like it's improper, but in fact it is.